Advanced Financial Modeling, Topic 18, Forecasting Financial Statements, Section 5. We're going to use non-normal distributions in our model that calculates free cash flows in at-risk. So let's talk about distribution. So far in this course, we've only used the normal distribution. So let's think about distribution. Distributions are assumptions about the future dispersion or distribution of some output, say the expected stock return. When we look at asset returns for, say, stocks or even commodities or currencies, we generally assume a normal distribution. You think about what's it look like to have a normal distribution. It's a single peak, it's symmetric, and the tails seem to go on forever, even though low and low probability event. So it's not bounded. So it's unbounded, it's single peaked, and it's symmetric. But you can choose lots of different shapes. You don't have to have a shape that looks like a bell. You could have a shape that looks more like this. And the only difference of this looks like it's bounded. It doesn't go on forever, but it is single peaked. But what happens is it's a little bit fatter here. It's a different type of bell. So a lot of bells look like this, and some bells look more like domes. So I could have specified a distribution that looks more like maybe this beta or beta general distributions. I could have distributions that are simple coin tosses. So a Bernoulli or benign distribution is simply zeros and ones. I could have distributions that sort of look like normal, but they're skewed to the right or left. I can look at this chi-squared distribution. Looks like it's really skewed to the right, but looks like it's not to the left. All right, so you can have all kinds of distributions. We've just picked the normal distribution to be the one which we use for most of our assumptions. Also, that peak could come up to a single point like that, or it could be more of kind of domed at the top. So all I'm trying to say is we can have lots of different shapes to assume for a future distribution. Now, two that I use a lot in corporate finance applications is not normal distributions, because it's really hard for me sometimes to forecast what is the standard deviation of sales and assume normality. What I generally would use are two of my favorite distributions to use, kind of my go-to, are triangular and uniform. So triangular distribution, if you think about it at the highest level, a triangle and a bell look almost the same, right? They're very similar. So what's the difference? They have a single peak, except it's bounded, and a triangle doesn't have to be symmetric. They look like this. So, and it could be really fat or really skinny. So I could just specify that it's not a bell, it's a triangle. Or I can just get away from the assumption of a bell-shaped curve or a triangle. In other words, get away from single peak and just use uniform distribution. So I can just say some number is going to be between this level and this level, but every one of them is just as likely. It's not going to be some peak. So let's make some assumptions on our last spreadsheet we generated. We're going to forecast free cash flows again, but I want to get a Monte Carlo simulation of those cash flows and then think about making some assumptions about the distributions of two of the outputs. So go to our spreadsheet. Here's my model that we did last time. I just put it in a single column here. So I have my free cash flows estimated at 150, my FCFF. But I want to make two assumptions related to two of the parameters, namely revenue sales growth and CapEx sales growth. So I'll just make those a little different color for now to highlight those. And what I want to do is I'm going to assume that revenue growth, I expect 20%, but I'm gonna just say that it's going to be triangularly distributed with a min of 5%, most likely of 20%, and a maximum of 25%. And then I'll assume a uniform distribution for CapEx between 15 and 25. And then I'll further assume there's a correlation between sales and CapEx of 0.5. Actually, let me put that 0.5 in there. So let's go ahead and run my simulation. And what I'm going to do, I need to specify these two as inputs. I'm going to make this an output. So the first thing I'm going to do is make sure I got at-risk running. So I'm going to run at-risk. right, close that. I'm going to go to at risk, and I'm going to click on my B150. I'm going to add output. That's the first thing I want to do. And I want to specify these two as inputs. So I'm going to go click on revenue growth. It's another way of actually inputting at-risk distributions is click on a number, click on define distribution, select the shape. So let's go ahead and select triangular distribution, triang. Now I need to put parameters in for the triangular. I need to say what the peak is, the most likely number, the min and the max. So I'm going to click right here. See where it says assign Excel references as arguments. Now I could type in numbers here, but I'm just going to have it linked to Excel. And it's asking me the min, D4, the most likely, E4, and the max, F4. Now static value, I'll leave that as 0.2. What that means is when you're not running Monte Carlo simulations, what is going to sit in the cell that's going to generate the static value of 150 down here? And I'll just leave that. So I'm going to click right there in the top right, and here's my triangle I just created. Notice it's bounded between 5 and 25, has a single peak, and this is not symmetric. And I'm going to hit OK. Now for CapEx as a percentage of sales, I'm going to use a uniform distribution. So I'm going to go define distribution. While I'm sitting on that CapEx cell, I'm going to select uniform distribution. I'm going to click on assign Excel references, and all I need is a min 15, a max 25. I'll leave that as my static value. Close out of that, hit OK. So now I have two inputs, one output. If I go to my at-risk window and click on model window, you'll see I have two inputs, one output. Now the last thing I want to do is I want to add my correlation matrix. Now if I don't add a correlation matrix, it's just going to assume that they have a zero correlation. So what I want to do is actually add a correlation matrix. I'm going to assume that my CapEx and sales are related, and I'm going to use a 0.5 correlation. And that could be based on historical values. So I'm going to select both my inputs, right click, correlate, create new matrix. I need to put them in the same order. So notice I have sales and CapEx. So I want to make sure that's sales and CapEx. That looks good. I'm going to then right click, copy coefficients from Excel. I'm going to specify where my correlation matrix is. Hit OK. Oh, let me go back. Copy coefficients. Select. Hit OK. Look at a little error here, so let's see what's happening here. Select cells with coefficient values. Okay, worked that time. I now have my 1, 1, 0.5, 0.5. Last thing I need, at risk needs you to put this somewhere in the spreadsheet. So I'm going to click right here, location, and I'll just put it down here. Hit OK. OK. Oops. Try that one more time. I'm going to go to my model window, select my two parameters, copy or correlate, create new matrix. I'm going to right click, copy coefficients, select. I'm going to hit OK a bunch of times where it says location. I'm going to select that. I'm going to put it down here. Okay. Okay. And this is the actual correlation matrix that at-risk is going to use, even though it copied it from here. And now I can run a correlation. So let me put at-risk out here. I'm going to click on my free cash flows. I'm going to start my simulation. I'm going to do 10,000 iterations. Start. Notice it's going to give me a default here, my 90% confidence interval. So I'm now 90% confident that free cash flows will be between 122 and 171. And I could also look at things like, what's the probability that we make 125 in cash flows? Say 125. It looks like it's about a 91% chance we're going to get at least 125. So this allows us to not have a single point estimate. We can think about what is the possible range of free cash flows, so it makes us make better business decisions. And the last thing I'll do is I'll put, instead of having to type numbers in my graph, from my graphs up there, I can use a couple at-risk formulas. Equals risk percentile, put in an output, comma, 5%. That's going to tell me my 5% left tail. If I anchor that output and copy it here and ask for the 95%, I'm 90% confident it's between 120 and 171. In other words, this is my 5% worst case. This is my 5% best case. I can also use the risk target. Equals risk target. Go ahead and put in my output, anchor that, comma, 125. And that's going to tell me the probability it's less than 125. I'll copy that. If I change that to risk target D, it's going to tell me the probability that's greater than 125. So in this topic, we used non-normal distributions to estimate free cash flows and then calculate some probabilities of certain levels. That is the last topic.